Hi everyone. In the last few lectures, we started our discussion on the step response of differentiators. Mainly, we focused so far on the step response of inverting differentiators. To complete the discussion, I thought we'll spend another few lectures on non-inverting differentiators. Shown here in the circuit is an opamp based RC non-inverting differentiator. We have already analyzed the transfer functions of such circuits before, and you can easily analyze it. The input is applied at the non-inverting terminal, output is taken here. So the transfer function of this circuit is given by 1 plus Z2 by Z1, Z2 being the impedance in the feedback path and Z1 being the impedance at the inverting terminal. So that will give me 1 plus SRC. So if you look at this expression, the SRC term here denotes the differentiation part, the non-inverting differentiator part. Okay, so this is not a pure non-inverting differentiator. You also get a constant term along, a proportional term along with it. So, but since it's a circuit that we have all analyzed before, so I thought we'll do the transient analysis for this circuit. So it's given the saturation voltages of for the op-amp in this circuit is plus minus 15 volts. The RC time constant for this differentiator is 1 millisecond, and the value of the resistance is 1 kilo ohm. You are supposed to find out V0 of t, the output voltage, and the inverting node voltage Vx of t for all time, given a step input of magnitude of step value delta V volts is applied at the input to this circuit. Okay, so what I'll do here is that first I'll analyze this using intuitions. We will predict what happens to the circuit at the boundary conditions, which is what happens at t equal to 0 and what happens at t equal to infinity. So we already discussed for a lot of circuits, even active circuits, using intuitions you can easily predict the steady state behaviors and the sudden transient behaviors. So shown here is a circuit with, this is something we have already done, so I'm just using the same analysis techniques here. So first, when the input arrives suddenly at t equal to 0, assuming the cap will have 0 charge stored across it, and then you can see the voltage across the cap cannot change instantaneously, so it will act like a short circuit. So if the cap acts like a short circuit, that amounts to grounding your, which means your inverting terminal node voltage will also be at ground, and the circuit will reduce to something like this. So it will look like as though the op-amp is an open loop, and a huge input differential voltage of delta V volts appears at the input of the op-amp. Okay, there is no feedback, and this is not surprising. This should be expected in differentiator circuits. We said differentiator circuits don't have transient feedback, they tend to have feedback in the steady state, negative feedback in the steady state. So when a huge positive input voltage is applied at the differential input of the op-amp, the output goes to plus Vsat. Okay, so initially the output jumps to, it starts off at 0 and jumps to plus Vsat. What happens at t equal to infinity in the steady state? Whenever you have a resistor and capacitor circuits and you are applying DC inputs, so the step input in the steady state will look like a DC input. Eventually the capacitor would have been charged to some voltage and it will act like an open circuit, which means the current flowing through the cap will be 0. So the current flowing through the resistor is also 0. And if you look at this op-amp, the op-amp will reduce to a structure that looks like this. It will just reduce to a voltage follower mode as shown here. Okay, that's what is shown here. The op-amp circuit will reduce to a voltage follower mode. So the output will simply follow the input. So if the input voltage is at delta V volts, output will also be at delta V volts. And of course the inverting terminal will also come to delta V volts. So your output starts off at Vsat and eventually settles to delta V volts in the steady state. Now how does it reach there? What happens in between? That's what we will do this analysis for, a more rigorous analysis for. Whether the output reaches delta V as a first order discharging, or does it go through an abrupt change somewhere? How does it reach delta V? That's what we are interested in knowing. So yeah, so let's start the analysis. So first we will find what is the output voltage for t equal to 0 minus. That is just before the step input is arrived. What is the output voltage of this op-amp? Okay, because that will set the initial condition. Once you know the initial condition, then we can predict how the circuit is going to behave once the step arrives. Now, before the step arrives, the input voltage is 0 because it's a step input. It starts off at 0 and suddenly jumps to delta V volts at t equal to 0. So before the step arrives, the input can be treated as 0 volts. We can apply the same logic that we applied for finding the steady state value after the step arrives, sometime before. We can argue that before the step arrives, the circuit has reached a steady state and the capacitor is acting like an open circuit. So if the cap is acting like an open circuit, then the circuit will reduce to a voltage follower mode. So the output will simply follow the input voltage. So that will also come to 0 volts. Okay, the current flowing through the resistor is also 0. So this node voltage will also be, the inverting node voltage will also be at 0. So V naught of 0 minus will be at 0 volts. Okay, so now we'll analyze the circuit when the step arrives. At the instant t equal to 0, a step of magnitude delta V volts is applied to this op-amp based circuit. Suddenly when the input arrives at this non-inverting mode, the capacitor's voltage cannot change instantaneously. So the inverting node voltage will stay at 0 volts. So that amounts to applying a huge positive voltage at the input of the op-amp. So the output will saturate to plus Vsat. So suddenly it was initially at 0 volts, at 0 minus, and then at 0 plus it would have jumped to Vsat. So that's what I've shown here. The output suddenly starts from 0 and jumps to directly to plus Vsat, which is the output is simply saturated. So on a transfer characteristics of an op-amp, I'm plotting the differential input to the output. You can see the circuit, the op-amp operates in this point. That is, the op-amp is operating in the saturation region where the incremental gain of the op-amp is 0. So even if I change this node voltage Vx, that the op-amp is not going to respond to that. Okay, so therefore the op-amp is no longer in the negative feedback mode, and this circuit, once the output goes to Vsat, I can just remove the op-amp and treat it like an output DC voltage source of 15 volts, Vsat volts. So that's what I've shown here. Since the op-amp is removed, the circuit reduces to a simple RC circuit in series with a voltage source of Vsat volts. So this here is your op-amp output, and this node here is Vx of t. Now this is a simple first order RC circuit, and we know how to find the node voltage Vx of t for all time, right? So you need to know the initial voltage across the cap, which is 0 volts. You need to know the final voltage across the cap, and how do you find that? In the steady state, the cap will act like an open circuit. The current through the circuit will become 0. So the voltages across the resistor will become equal. So the steady state voltage of Vx of infinity is plus Vsat. So let's use that expression. So Vx of t will simply be given by the final voltage minus initial voltage, which is Vsat, times 1 minus e power minus t upon tau. This is the voltage of Vx of t. So now op-amp is out of saturation, and the node voltage Vx slowly starts to rise. As the node voltage Vx increases, what is happening here is that the differential input to the op-amp, Vd, which is the differential input to the op-amp, is reducing. What is the differential input to the op-amp? V plus minus V minus, and V plus in this case is delta V minus Vx of t. This is our differential input to the op-amp. What is of interest to us? When the differential input to the op-amp becomes 0, then the op-amp will come into the high gain region. Okay, and the time at which the op-amp reaches this can be found by this expression. So all you need to do is find out the node voltage Vx of t and find the time at which it reaches delta V volts. When Vx of t reaches close to delta V, the differential input reaches close to 0. So the op-amp will now come into a very high gain region. So you can equate delta V and Vx of t and find out the time at which it reaches that value. So that will be tau ln of Vsat by Vsat minus delta V. You can easily verify this result by substituting delta V to be equal to Vsat by 2. assuming the input step voltage is half of the saturation voltage, you can see that on time, the time at which it reaches delta V will simply reduced to tau ln 2. And this is a familiar result to all of us. For any first order system, to reach its half value, or half of its final value, the time it takes is tau ln 2 seconds. So we have just verified this result. Okay. For any general delta V step input, the time it takes to reach delta V volts is simply given by tau ln of V sat upon V sat minus delta V. Okay. So that's the expression for finding it. Now what happens when the circuit reaches this, when the node voltage Vx of t approaches delta V? When it approaches delta V and it increases slightly above delta V, what happens to the circuit? The output node voltage will now start decreasing. Okay, it will try to go to minus Vsat. But as it is decreasing and decreasing, when it reaches a value of delta V volts, when the output voltage reaches delta V, the capacitor voltage is close to delta V, we can treat it more or less equal to delta V. What happens? The current flowing through the resistor becomes 0. If the current flowing through the resistor becomes 0, then the capacitor voltage will stay put at delta V volts. It will not change anymore. The input to the op-amp at the non-inverting terminal is delta V volts. The differential input is 0 and the output has come to delta V, and the state of the circuit will no longer change, which means the voltages and the currents in the circuit will no longer change. At this point, the circuit will reach a steady state. You can easily verify what happens if by showing, assuming the op-amp has a finite DC gain, and show that if you guys think about it a little bit, the op-amps, assume I'm just exaggerating this region, the high gain region of the op-amp. When this output node, when the node voltage Vx of t, approaches delta V minus V sat upon A. Okay, when Vx of t becomes very close to delta V, it's approaching delta V, but it's slightly lower than it, lower by V sat by A volts. What happens to the differential input? Your differential input is given by delta V minus this. So delta V minus V sat upon A. So which will be V sat upon A. So the differential input of the op-amp becomes exactly equal to V sat upon A. So now the op-amp will enter the high gain region. Okay. So from that point onwards, if your node voltage Vx, let's say it changes by a factor of epsilon, that is your Vx of t increases by a factor of epsilon. So what will happen to your differential input? It will decrease by a factor of epsilon. So your differential input will decrease. On this axis, I'll be moving inward by a factor of epsilon. On x-axis, if you move by epsilon units, on y-axis you will move down. From this point, you will move down by A times epsilon, right? Because it's a very high gain region. You will move down to A times epsilon. Okay, until finally the output voltage will reach delta V volts when the error becomes, when epsilon becomes equal to delta V upon A. So when your node voltage Vx of t reaches delta V minus delta V upon A, your circuit will more or less reach the steady state. Okay, so at this point, what will happen to the circuit? The output voltage will come to delta V, and this node, the voltage across the capacitor is now equal to delta V minus delta V by A. So the differential input to the op-amp is delta V by A. Multiplied by A, you get the output voltage of delta V volts. Now if I let A tend to infinity, okay, if I let A tend to infinity, that's it. You will get the steady state operating point. If you let A tends to infinity, all the nodes, the input node, the inverting terminal node, and the output node will all come to delta V volts. And that will happen instantaneously. If A tends to infinity, this shift of the movement from V sat by A to epsilon will happen instantaneously. So that's what I've shown. Vsat will suddenly fall to delta V volts. So that's what happens here. Your output signal, if I plot the output signal as a function of time, initially it will be at 0 volts. At t equal to 0 plus, it will jump to Vsat. It will remain constantly at Vsat volts for t on seconds. Then it will fall down to delta V volts. Okay, this is how the circuit will look like. It will have a jump of Vsat and then a sudden jump of a negative jump. Then the voltage will suddenly drop or fall to delta V volts and remain constant afterwards. Okay, so this is how the output will look. Does this result make sense to us? Okay, we need to analyze that as well. So what I'll do is I'll take this waveform and split it up as two waveforms. If you see this waveform, I can split it up as a step of value delta V plus a small pulse of value Vsat minus of peak value Vsat minus delta V. So this is what I can do. The output waveform can be written as a step signal, the same input step signal of magnitude delta V volts, plus a pulse signal whose width is t on seconds and the amplitude is Vsat minus delta V. And we just know what the expression for t on is, right? We just derived some moments back. Now if you observe this result, right, this circuit, the circuit we are talking about, is actually the non-inverting integrator it also has a proportional term. The transfer function is 1 plus s tau. The constant term denotes this. Okay, the output is suddenly changing at the constant term tells you that the output should exactly follow the input for all time. Then there is a derivative term. This pulse signal of magnitude Vsat minus delta V is a response to the derivative term. So now it makes sense. You have a term, the output has a component which is simply the same representation of the input, because that's what the transfer function of the circuit says. The transfer function says it should be 1 plus s tau. This is your transfer function, which means your V0 is equal to Vi of t plus some other term, which is dependent on the derivative of the input. Okay, and that term, the derivative term looks like this. So just wait for another lecture. I'll try to relate what should we see. Ideally, derivative of a step should be an impulse. But because we are assuming the opamp to have a finite saturating characteristic, we end up getting a narrow pulse, a pulse of duration t on seconds. Okay, the shape of this pulse should have been ideally an impulse. I should have expected an impulse at this point, because that's what the transfer function tells me. But because if the opamp was ideal with infinite gain and no saturation voltage limits, then it would have just produced an impulse. But here it produces a pulse of finite width and amplitude, and the amplitude is Vsat minus delta V. So the result actually makes sense. It's not completely alien to us. And if you guys recall from the previous lecture for inverting integrators, that's what happened, right? When you fed a step input for an inverting differentiator, the inverting differentiator transfer function was minus s tau. Okay, it was just minus of tau times d Vi by dt. So when you applied a step input, the output was a negative pulse. So that's what you see here. Because this is a non-inverting integrator, for a positive step input, you are seeing a positive pulse. Okay, a pulse of positive amplitudes. Okay, so that's it. And if you assume delta V equal to Vsat, then you will actually see that you can do the analysis yourself. The output will reach Vsat and stay constant at Vsat forever, because the maximum monode voltage that a opamp can have, opamp's output can have, is plus Vsat, which means the capacitor voltage will never increase more than Vsat. So there is no scope for the output to change its polarity. So once it reaches plus Vsat at t equal to 0, it will stay there forever. The next lecture, we will talk about RL differentiators.